Here we want to find the partial derivatives of a function of more than two variables. This is a function of three variables. And then after that, we will look at how to examine functions whereby is it possible to simultaneously solve for the partial of f with respect to x, the partial of f with respect to y, setting both of those partial derivatives equal to 0. But first, let's look at this. So we find the partial derivative here of f with respect to x, and just use my short notation. This is 6xy minus 5yz. Find the partial derivative of f with respect to y. This is 3x squared minus 5xz plus 10z squared. Then find the partial of f with respect to z. This is negative 5xy plus 20 plus 20yz. So do you see that for the partial of x of f with respect to x, that derivative is 2 times 3, 6x. Y is a coefficient. And then we take the derivative with respect to x here. That becomes negative 5yz right here. There's no x over there, so this is treated as a constant with respect to x. And then in like manner for y, the derivative here is 3x squared, because 3x squared would be a coefficient with respect to y. And then the derivative with respect to y for this middle term would be negative 5xz. And then the derivative here with respect to y is just 10z squared. And then likewise for z. What about this one? The partial of w with respect to x. If you see the symmetry from a problem that we did before, you know that that this would be x over the square root, and then the partial of w with respect to y would be y over the square root, and then likewise for z. But I can show it to you, but after a while you kind of see the pattern. Just go ahead and just write the answer. So this becomes 1/2 times the expression x squared plus y squared plus z squared, and that's raised to the negative 1/2 power times the derivative of the inside with respect to x, that's 2x. So here this is just x all over the square root. Likewise, the same pattern happens with y, the partial of w with respect to y. Then likewise the partial of w with respect to z. Here we find the first partial derivative, set them equal to 0, and then it says solve them simultaneously. So basically, solve the system of equations. Well, you can't see that now, but let's see. The partial of f with respect to x, this is 2x plus y minus 2. You're going to set that equal to 0 according to the instructions. So when you do that, this implies that we have 2x plus y is equal to 2. Now the partial of f with respect to y, this is y plus 2y plus 2. It's set to equal to 0 from the instructions. So this implies that we have y plus 2y is equal to negative 2. So we have a system of equations that we solve. So to solve this system, a couple of ways you could do it. But if you take the first equation and solve for y, it gives us y is equal to 2 minus 2x. We replaced the y in the second equation with that expression. And so this is 2 minus 2x. I wrote something wrong here. Take this partial of f with respect to y, that's x plus 2y plus 2a. You know, I heard you saying that. Thank you. Just through the transmission of the airways. No, I'm just joking. I messed up. Okay, this is the x. That's going to change. So this is an x. It's an x there. So again, we have from the first equation y is equal to 2 minus 2x and x plus 2y is equal to negative 2. Replace this y here with 2 minus 2x. And so this implies then that we have x plus 2 times parentheses 2 minus 2x is equal to negative 2. So we get x plus 4 minus 4x is equal to negative 2. And this implies that we have negative 3x is equal to negative 6. And we get x is equal to 2. So if x is equal to 2, we have y is equal to 2 minus 2x. 2 minus, these computers trying to write on the screen is not for a left-handed person. 2 minus 2 times 2, using that. And so we get negative 2 for y. And so we get x is equal to 2 and y is equal to negative 2. So find all values of x and y. So it's not a point per se. That's it.